Welcome to Math 103 College Algebra at Central Connecticut State University. Just a quick little video here reviewing lecture notes that I've used in class. So we've talked previously in class about a polynomial function of degree n can be represented by this expression, okay? And I don't want you to get freaked out by that. We've talked about this before, that if I say f of x equals ax squared plus bx plus c is my typical parabola. A cubic function, f of x is ax cubed plus bx squared plus cx plus d. And notice that we have, with a cubic, we start with x equals 3, 2, 1, and 0 as we go down. This is just, this thing is just a way to say we're going to start with x to the n, and then notice that each additional term, the degree is dropping by 1 until you get down to that constant. Because we don't know how many terms we're going to have, we're not going to start with a and then go to b and c and d. We're just going to let every coefficient be a. But then we don't know how to distinguish them. So we have a for the nth degree term, a for the n minus 1th, a for the n minus 2nd degree term, the coefficient a sub 2 for the quadratic, the coefficient a sub 1 for the linear, and the coefficient a sub 0 for the constant term. So it looks messy, but we never see anything like that. Okay, what we're going to talk about in this video, and again, it's a quick summary of what we've covered in class. We've got the graph of a polynomial function, and we're going to focus in this video on the turning points and on the end behavior, okay? The turning point occurs whenever the graph changes from increasing to decreasing or from decreasing to increase. So for example, and real quick, and I'll revisit this again later, again, a quadratic is a concave up or a concave down parabola. You notice here where the function is decreasing, it stops decreasing, and then it starts to increase again. The point where that direction changes is called a turning point. And then end behavior of a function is the behavior of the function at the ends. So the ends here pointing up, okay? So we're going to look at either as x approaches negative infinity, or as we look farther to the left, x approaches positive infinity as we look at the graph moving to the right. What are the y values doing? Is the graph increasing or is the graph decreasing? Okay, so first we have a constant function, f of x equals a. The graph of a constant function is just a horizontal line. There are no turning points, and then the end behavior, as x approaches negative infinity, y is approaching a. It's not going up, it's not going down. As x approaches a positive infinity, y is again approaching a. There is no change. So for example, let's suppose I have the function, let me get rid of this graph here for a second. Suppose we have the function f of x equals 3. The graph of that function, 1, 2, 3, is a horizontal line, y equals 3. As we look farther and farther and farther to the left, as x is approaching negative infinity, my y values are 3. As x moves toward positive infinity, my x values are 3. So notice that whether x goes farther and farther to the left, or, that's an F, or farther and farther to the right, y is approaching 3. Y is approaching 3. So as x goes farther and farther to the left, as x approaches negative infinity, y is going to be approaching a. As we go toward positive infinity, y is approaching a. Okay, so that's a quick look at a constant function. If I have a linear function, okay, and I'm going to assume in all of my examples that a is positive. So I'm going to talk, first of all, a is positive. If a is positive, we have what we call an increasing function. So a linear function, if a is positive, is going to be going up. Actually, I'm going to make that graph smaller. So if I have a linear function, if a is positive, the graph would be increasing. If a is negative, the graph is decreasing. Okay. Notice the graph does not turn. There are no turning points. So there are none. Okay? The end behavior we're going to look at as x approaches negative infinity and as x approaches positive infinity. What we mean by as x approaches negative infinity is we look farther and farther and farther to the left, notice that the graph is going down. So y is approaching negative infinity. As x gets farther and farther to the right, notice that the graph is going up. So as x approaches positive infinity, y is approaching positive infinity. The same thing if a is negative. To examine the end behavior, we're looking as x approaches both positive and negative infinity. What's y doing? It's kind of like a yes-no question, a true-false question. Notice as x approaches negative infinity, as we go look farther and farther and farther to the left, the y values are going up. So y is approaching positive infinity. As we look farther and farther to the right, as the x values are approaching infinity, the function's going down, so y is approaching negative infinity. The end behavior is always y is approaching positive infinity or negative infinity. In a quadratic function, if a is positive, we have a parabola that's concave up. If a is negative, we have a parabola that's concave down. There's one turning point. The turning point is at the vertex. Okay, one turning point. The end behavior is again as x approaches negative infinity. What's y doing? What is the y approaching? As x approaches positive infinity, what is y approaching? And in this, we're going to look at both when a is positive as well as when a is negative. So as x is approaching negative infinity, what's y approaching? As x approaches, which infinity is y approaching? Notice for the parabola, if a is positive and the quadratic is concave up, again, there's one turning point at the vertex. As we look farther to the left, the graph is going up. So y is approaching positive infinity. If we look farther to the right, the graph is going up. So y is approaching positive infinity. This is all we're looking at as far as end behavior. Notice that if a is negative, the quadratic is concave down. Pretty ugly pictures here. Let me erase both of those and try again. The quadratic, if a is negative, is going to be concave down. Whether we're looking to the left or to the right, the end behavior is pointed down. So y is approaching negative infinity, both as we look farther to the left as well as when we look farther to the right. Okay. In this video, we're just going to go through the different degrees. Notice we have a cubic function, third degree. First, we're going to look at what is the graph going to look like if a is positive. The graph is going to look something like this. And if a is negative, the graph is going to look something like this. Notice that overall the function ends increasing when a is positive. Notice the graph ends decreasing when a is negative. That's true for all polynomial functions. This graph is going to start by coming up. Here's a turning point where the graph stops increasing, starts decreasing, and another turning point here. So there's 1, 2 turning points. If I am looking when a is negative, the graph is decreasing, it stops decreasing. So here is a turning point. It increases again, so there is another turning point. A cubic function, third degree, 2 turning points. To look at the end behavior, again, when a is positive, we're going to look at as x is approaching negative infinity or as x is approaching positive infinity. If we look farther to the left, we look farther to the right. What is y doing? As we look to the left, notice that y is approaching negative infinity. As we look farther to the right, y is approaching positive infinity. When a is negative, we're going to look to the left and we're going to look to the right. If we look to the left, notice that as we look to the left, y approaches negative infinity, the y value goes up and up, so that'd be a positive infinity. And then negative infinity as we look to the right. What you should notice is that in the odd degree polynomials, the end behavior is in opposite directions. Okay, so let's look at a quartic real quick. Again, let's look at if A is positive, what's the graph going to look like? And if A is negative, what's the graph going to look like? If A is positive, the graph is going to look a little bit like a W. If A is negative, it's going to look a little bit like an M. Okay. Notice the degree is 4. There are 1, 2, 3. 1, 2, 3 turning points. If A is negative, there's 1, 2, 3 turning points. 3 points where the graph changes. So the number of turning points is the same whether the A is positive or negative. For the end behavior, we're going to look both as x goes farther to the left and as x goes farther to the right, both when A is positive as well as when A is negative. So here's x goes farther to the left. Notice that the y values go higher and higher. Y is approaching positive infinity. If we look to the right, the y values are going up, so y is approaching positive infinity. We look to the left, we look to the right for the negative. When A is negative, notice the graph points down in both directions. So both as we go to the left and we go to the right, y is approaching negative infinity. Like I said before, when the degree is odd, what you should notice is that these end behaviors are opposites. Y is approaching positive infinity, negative infinity. Y is approaching negative infinity or positive infinity. Those are going to be opposites of each other. However, for an even degree function, notice if y is approaching positive infinity, it's going to be in both directions. Negative infinity in both directions. Okay? So, even degree, the end behavior are pointing in the same direction. Odd degree, they're going to be pointing in opposite directions. So let's look at the quintic, okay, for a fifth degree polynomial function. Odd degree, I'm going to expect my end behavior to be in opposite directions. Also, since I have fifth degree, I'm just going to guess that there's going to be 4 turning points. If A is positive, 1, 2, 3, 4 turning points. 1, 2, 3, 4 turning points. Notice the end behaviors are in opposite directions. I just pointed, you probably didn't see me point. If A is negative, 1, 2, 3, 4 turning points, or 1, 2, 3, 4 turning points. For the end behavior, again, we're going to look as x approaches negative infinity. As x approaches positive infinity, what's y doing? Notice, if A is positive, if we look farther to the left, y is pointing down. If we look farther to the right, the graph is pointing up. That's a pretty ugly infinity. I'm going to fix that. And then if A is negative, notice we're going to look again as x approaches negative infinity and as x approaches positive infinity. Notice if we look to the left, the graph is pointing up. Y is approaching positive infinity. If we look to the right, the graph is pointing down. We're approaching negative infinity. Okay, so it's that simple. If I look at a graph here, given the function at the right, how many turning points are there? There are 1, 2, 3, 4 turning points. How many x-intercepts are there? There are 1, 2, 3, 4, 5. Okay, that looks like it touches the x-axis. There are 5 x-intercepts. 1 is a double root. The sign of the leading coefficient I know is negative because the graph ends pointing down. The lowest possible degree, there are 5 x-intercepts, there are 4 turning points. The lowest possible degree of f of x is 5. Okay? So in this next one, it says to use the graphing calculator. Graph f of x equals x cubed minus 2x squared minus 5x plus 6. And we're going to graph that. I'm going to hit my zoom 6 for a standard window. Here's what that graph looks like. Identify the x-intercepts. Okay, there's an x-intercept here, here, and here. They look to be at x equals -2, 1, and 3. To find those, we could do second calc number 5 intersection. Okay, I'm sorry, that's not what we want. Second calc, what we want is number 2, 0. I'm sorry, second calc number 2, 0. We want to find this x-intercept. So we're going to cursor to the left of that x-intercept, press enter. We're going to cursor to the right of that, press enter, go back somewhere in between, press enter, and you'll see we do have an x-intercept at -2. If you repeat that process, you should find an x-intercept at 1 and at 3. Okay. To approximate the coordinates of the turning points, I'm going to do the same process. To find that maximum, and that's a relative maximum, second calc, we want to find number 4, the maximum. So if this is the maximum, then we're going to find, notice the calculator says calculate maximum. To find that maximum, I want my cursor to be to the left of it. It is. I press enter. Now I want a cursor to the right of that. Press enter. Go back somewhere in between. And it looks like we have a maximum. I'm sorry, we have a turning point at -0.786. 0.786, and the y value is 8.29. That's a turning point. It's also an extrema, -7, 8.6. Your extrema will occur at turning points. The other turning point is this minimum right here. Second, calculate number 3, the minimum. Now we want to be to the left of the minimum somewhere. This is about good. Press enter. Move to the right of that. Press enter. Move back somewhere in between. And we have a turning point at 2.12. And the y value is -4.06. Again, that's another extrema, 2.12, -4.06. So notice that the extrema occur at the turning points. One other thing I'm going to do is I'm going to label that this one was a max, this one, this is a max, and by max I mean maximum, and this is a min, and by that I mean a minimum. They're both relative. Okay. Real quick, last thing, going to throw this in here. Piecewise functions, we've talked about this before, just a quick review. Notice we want to use the 2x minus 3 if x is less than or equal to 2, x squared plus 1 if x is greater than 2. So f of -1, -1 is less than 2, so I have 2 times -1 minus 3. -2 minus 3 is -5. F of 0, 0 again is less than 2, so that's 2 times 0 minus 3. 0 minus 3 is -3. Now f of 2 is still less than or equal to 2. So 2 times 2 minus 3 is 1. You might say, when do I use the bottom part? You use the x squared minus 1 when x is greater than 2. 5 is greater than 2, so f of 5 is 5 squared plus 1. 5 squared is 25 plus 1 is 26. Last thing in this video I want to touch on is how do I graph that function? Okay, I'm going to go way over here. We've already got these points. Okay, we've got 0, -3. So here's 0, -3, -1, -5, and 2, 1. So it looks like we have this line here, and I should label those points. If I put 2 into this part, okay, I would get 2 squared plus 1 is 5. So at 2, 5, I'm going to have an open circle. Because we don't want to include that, but that's going to be an open circle. And then we can put in other points. What if x is 3? 3 squared is 9 plus 1 is 10. So we'd have 3, 10. Notice that this is quadratic, so this is actually going to curve upward as a parabola. So that's graphed. Okay? So there's a quick look predominantly at polynomial functions and models. Specifically, we spent most of our time talking about turning points and in behavior. I hope that this was helpful, and I hope to see you soon in class.